you get the effective flange width. So you should not worry. I'm going to have one problem where you are supposed to compute the effective flange width. Okay? But here to start up, this effective flange width is given to you, and it is 1200 mm. The thickness of slab is 100 mm, so it means your thickness of flange is going to be 100 mm. All right, and the width of rib, that is your width of web, is 300 mm. And effective depth is given. So we do not have the data on overall depth. Directly effective depth is given as 560 mm. So this beam is reinforced with 4 number of 25 mm diameter bars. Now you are supposed to compute the factored moment of resistance, and the material which you are using is M20 grade concrete and Fe415 steel. So before starting, let us draw the cross section for the problem. How the cross section looks like. So you have a T-beam section. We have this effective width of flange as 1200 millimeter. The depth of flange is going to be the thickness of the slab, which is 100 mm. Okay, and this is reinforced with 4 numbers of 25 diameters. So here you have this reinforcement. This is provided on the tension side. So here this is 4 number of 25, and then you have this effective depth, which is going to be measured from the top of the flange with the CG of the steel, and this is given as 560. Right. Now, in order to compute the moment of resistance, I need to know the location of neutral axis. Okay. And you know by now that you can have 2 possible positions of the neutral axis. In one case, it may lie within the flange, and in the other case, it may lie on the web. And if it is lying on the web, again you have 2 more cases, depending upon the rectangular portion of the stress block, okay, where exactly it is lying. If it is lying within the flange, then you have reduced the thickness of flange formula, and if it is more than the thickness of flange, then you are going to consider the overall thickness of the flange. So you are familiar with that, I assume. So right now, since we need to compute neutral axis depth in order to compute this factored moment of resistance, and I do not know exactly where my this neutral axis is going to lie. So what I am going to do, I'm going to assume. So I'll assume, which I'm going to confirm later whether my assumption is correct or not. I'm going to assume XU less than depth of flange. So this is one of the method with which I'm proceeding. So what I'm doing, I'm assuming XU less than depth of flange, and also I'm assuming that your XU is less than limiting neutral axis depth or maximum neutral axis depth. And if I assume this XU less than XU max, it means that your reinforcement is yielding. It means your reinforcement is what? Yielding. So let us proceed. So first, what I'm going to do is I'm going to compute, since I'm saying that I've assumed my neutral axis is lying within flange. So this is the location of the neutral axis. XU. So this is based on my assumption. So this entire cross section is subjected to what? Compression. All right. So I would like to know what is the compression force in flange. Ultimate compression force in flange. So what is going to be the ultimate compression force in the flange? Average compressive stress, which is 0.36 FCK into shaded area. Shaded area is going to be what? Width of flange, effective width of flange into XU. So I can write 1200 into XU. So I can get this compression force in flange. Now next I'm going to compute what is the tension force. Since I have assumed XU is less than XU max, so my reinforcement is yielding, so directly I can write 0.87 Fy into AST. So I know how much is the area of steel. It is 4 number of 25 dia bar. So 4 into pi by 4 into 25 square. Okay, or as I said, if you know the approximate area of 25 dia bar, which is 491. So 4 into 491, you can do directly. So you can compute what is the tension force. Next, in order to compute neutral axis depth, you know you have to compare total compression force equal to total tension. Now, in this case, total compression force is going to be the compression force in the flange itself. So I'm going to equate these both. 0.36 into weight of concrete is 20 into 1200 into XU equal to 0.87 into 415. AST is 4 into 490. Okay. So from here you compute this XU. So how much is XU?
Sir, 82.07.
Okay, 82.07. Others, please confirm whether this is correct or not.
Yes, sir.
Okay, fine. So I have my neutral axis depth as 82.07 millimeter. Now I need to confirm whether this neutral axis depth, what we have computed, satisfies our assumption. So I can see here this XU is less than depth of flange, because depth of flange was 100 millimeter. So first condition is satisfied. What about XU max? What will be XU max? Any one of you, can you tell me? What will be limiting neutral axis depth? You have Fe415 steel. What will be limiting neutral axis depth?
268.8.
Okay,
268.8.
268.8, yes. So how you are actually getting that?
0.48 into D.
Yes, right. 0.48 times effective depth D, right. So if you are doing this 0.48 into effective depth was 560, and if you are getting 268.8, then that is. So here also I can see your XU is less than XU max. So our assumption is correct. I can see XU is also less than XU is less than XU max. So you can say that our assumption is correct, that is neutral axis lies within flange. Okay, so next what I can do, I can compute my moment of resistance. What is going to be my moment of resistance? Compression force into lever arm. So you have only force in the flange, you do not have a compression force in the web, because since my neutral axis is lying in the flange, so you'll have only compression force in the flange. So this is going to be multiplied with your lever arm. So lever arm is going to be D minus 0.42. So compression force in flange. So you know the expression which I have already written over here. So substitute everything and tell me what is the moment of resistance.
371.463.
Okay, 371.46 kilonewton meter. Again, anyone can confirm this answer, whether this is correct or not.
Yes, sir.
Okay. So we have 371.46 kilonewton meter as the answer. Now here you see this was the one of the approach I had assumed was like neutral axis is lying within flange. Like XU less than depth of flange, it means my neutral axis is within flange. But it was possible, like after doing these calculations, suppose if XU was 120 mm, then what you would have done? The assumption was wrong. Then you would have moved further. Now, in order to avoid this step, or in order to know whether my neutral axis is going to lie within flange or in the web, so other method with which you can do is, what you do, you compare the compression force in the flange. Okay, what is the total compression force in the flange, and also you compare what is the tension force in your reinforcement. If your compression force in flange is going to be more than the tension force, then you will say your neutral axis is going to lie in the flange. Okay, so please see the concept here. Rather than making this assumption, other way of ascertaining where exactly my neutral axis is lying. Another approach to know the location of neutral axis. So what I'm asking you is what you do, you compare the force, okay? You compare the compression force in the flange with the tensile force. So again here when I do this, my assumption will be what? Your neutral axis is less than xu max. So this one has to be there. So assume, which has to be confirmed. Why I'm assuming this? Because if I assume xu less than xu max, it means my reinforcement is yielding. And also, most of the times when you are designing your reinforced concrete structure, you always want to make sure that your tension reinforcement yields. Okay, so this assumption is always kind of valid. So always I'll to go for assuming xu less than xu. Next, what you do, you compare the compression force in flange with tension force in reinforcement. Okay, so if I do this, let us do this. So what is the compression force in the flange? It is going to be 0.36 FCK, effective width of flange into thickness of flange. So how much you get this compression force in flange? Substitute all the values. 0.36 grade of concrete was 20, effective width of flange was 1200, and thickness of flange was 100. How much you get compression force in a flange? And I'll tell you why I'm doing this. First, let me compute these values, then I'll give you the logic why I'm doing this comparison.
864,000.
Okay, so 864 kilonewton. So this is the compression force in flange. Next, what you do, you compute what is the tension force in your reinforcement. So since my reinforcement is yielding because of this condition, it will be 0.87 into 415 into AST is 4 into 491. So how much you are getting this tension force?
70910.
Okay, 709 kilonewton. All right. So here you can see your compression force in flange is more than the tension force. So it means that your neutral axis is going to lie within flange. So I'll write here, since compression force in flange is greater than tension force, neutral axis lies within flange. And I'll tell you the logic why it is. Now you please see, since your compression force and tension force both has to be equal. Okay, compression force and tension force has to be equal because if you are computing this moment of resistance, you know C into Z or T into Z, C and T both is going to be equal. So how you can reduce 864 to 709 kilonewton? Actually, I have to reduce this 864 kilonewton to 709 kilonewton. I cannot change FCK, I cannot change width of flange, but yes, I can modify depth of flange because this is not my neutral axis depth. I've assumed my neutral axis depth at the level of the flange. That's why here I have written depth of flange. It means that, so please see this logic. Try to understand what I mean to say. So right now, what you did is you have located your neutral axis over here. And what you did, you computed what is the compression force over here, CUF. And what you did, you computed the tension force. Now you know that your total compression force has to be equal to total tension force. Now what is happening? Your CUF is coming as 864 kilonewton, and your tension force is coming 709 kilonewton. So tension force is fixed. It cannot change because you have a grade of steel and area of steel fixed. Now I want this condition C equal to T. How I can get this condition? This condition can only be achieved if I shift this position of neutral axis, which I have kept at the flange level, a little bit above. With this, what will happen? my this area is going to reduce, and if my area is going to reduce, it is possible my 864 kilonewton will come down to 709 kilonewton. So it means my neutral axis depth is less than my depth of flange. Okay, so that's why I have written neutral axis lies within flange. So this is one of the check with which you can ascertain whether my neutral axis is lying in the flange or it is lying on the web. Okay, so what you have to do, you have to just compare the compression force in flange and the tension force. All right, and suppose if your compression force in flange is less than the tension force. Okay, so please understand, if compression force in flange is less than the tension force, it means you have to shift this neutral axis downward. So you say your neutral axis is going to lie in the web. Is this thing clear to everyone? If not, I will repeat it again.
Yes, sir.
Okay. So I hope this is clear to everyone. Now the same problem. Okay, now the same problem. What I'm going to do is, instead of 425 diabar, I will be using 525. Here you see what happens. Same problem. Okay, and instead of 425 diabar, I am using 525 mm diabar. So see now the steps again. Now for this, you have to compute the moment of resistance. All right. So what you have to do? So first I should know where my neutral axis is going to lie. So initially what I'll do is assume XU less than XU max. So you can follow in the same procedure here, whatever I have followed. Okay. So let us see that the other way of ascertaining where my neutral axis is going to lie. So let us compute what is the compression force if neutral axis is in the flange depth. So please see here, I'm writing, I have assumed my neutral axis to be here. So what is going to be your compression force? We'll write 0.36 into FCK into width of flange into your depth of flange, and we have computed this value. Okay, so you have already computed this value, so I'll not be doing it again. So how much it is? 864 kilonewton. So it is 864 kilonewton. Okay. What about the tension force? And here I will write simply CF. What is the tension force? Now tension force is going to be revised because there is 5 number of bars. So 0.87 into 415 into 5 numbers of pi by 4 into 25 square, which is 491. So how much is the tension force now?
886 kilonewton.
886 kilonewton. Now here you can see what is happening. Your compression force in flange is actually less than the tension force. So you need more area. So if you need more area, it means your neutral axis should lie in the. So from this comparison, since compression force in flange is less than T, neutral axis lies in the web. So I hope this point is clear without doing these computation, which I did here. First I computed CUF, then I computed T. So here I computed XU, then I compared XU with depth of flange, and then XU with XU max. So rather than going with that step, it is good that you compute what is the compression force if neutral axis in the flange with the tension force. And if you find the compression force in flange less than T, you will say neutral axis is lying in the web. Now when neutral axis lies in the web, again you have 2 more cases. Okay. What are the 2 more cases? So if you recall, you have seen the content, or if you have read the book, what are the 2 cases which you are going to experience? So the neutral axis is somewhere over here. So and this is your reinforcement. So you draw the stress block diagram. Here you will be having the tension force. Now please see, this is the rectangular part. Okay, this is the rectangular part. And this is the So this depth, you know, this rectangular depth, you know, it is 3 by 7 XU. So you get one of the case when neutral axis is outside flange. You get one of the case is what your depth of flange is greater than 3 by 7 times XU. Okay, so this is one of the case. The other case will be like this. This is the tension force. You have this rectangular part more than the depth of the flange. Okay, and this is the parabolic. This is 3 by 7 times neutral axis. Right? Let me mark this neutral axis vector. So this is your answer. So this is the other case. Your depth of flange is actually less than 3 by 7. So in this case, again, which case I should start with? I'm not very much sure whether I'm going to have this case or this case. I'm knowing my this thing. Neutral axis is lying in the web, but again I have two cases. So can you tell me which case I should go for? Whether I should go for case 1 or go for case 2? Can you suggest me which one? Which one case 2? Why you are saying case 2? Now please observe this. This is 886 kilonewton. This is 864 kilonewton. I just need how much force? 886 is fixed. So I need a very less magnitude of force, almost nearly 22 kilonewton. So for increasing 22 kilonewton, maybe this is not the depth. Your neutral axis, draw this again. So you can guess in that fashion. So maybe your neutral axis is somewhere over here. You need very less area in order to get that 22 kilonewton. Now, in this case, if I draw my stress block diagram, okay, in this case, if I draw my stress block diagram, it is possible that the parabolic portion, okay, you can see this is the parabolic portion. A part of the parabolic portion is going to lie in my flange. So based on this logic of mine, what I will do, rather than, yes, you can try with this, not a harm, but with this logic, what I will go with this case. Okay, with this logic, I will go with this case. So anyway, because I need to ascertain anyway, I'll be ascertaining it. So if you want, you can go with this, but in order to avoid a number of calculation, what I want, I'll go with this particular case based on this particular logic. So I'll write here assuming. So anyway, I have written over here, neutral axis lies in the web. So now I know neutral axis lies in the web. I again having two more cases. So I'll write assuming. So I'll write again this XU less than XU max, which I'll be confirming it. And also I'll write depth of flange is greater than 3 by 7 times XU. So this is my case. So this case, what I am doing, please observe this. So anyway, I'm not going to consider my tension side. So this one I'm considering splitting into flange part, okay, and the web part. And here you have concrete, which is in tension, and this is your neutral axis. So if you are not remembering the formula, you should not worry. You can draw this sketch. So you have this flange part. Okay, you have this flange part. So I would like to know what is a CUF. Okay, I should know what is this CUF. So can you tell me what will be CUF?
0.45.
Yes, yes, it is going to be 0.45 FCK into this width. Okay, width of flange minus width of web into reduced depth of flange wire. Okay, because if I see this flange part, in this flange part, the stress block is like this. Okay, it is like this. For some portion, it is rectangular, and for some portion, you have what? This parabolic portion. So what code has suggested? Code has suggested that what you do, rather than considering this entire area for computing this compression force, you consider the reduced depth. Okay, this YF, and in this YF you are assuming the stress to be constant of 0.45. This is what you have. All right. So you have this compression force in a flat, and what is YF, which code has given, and you'll find this YF in annexure G. Okay, so you please open ISO 562,000. There you'll find the value of YF. So what was the value of YF which was specified?
0.15 XU
0.15 XU
plus
plus
0.65 dm.
okay, 0.65 depth of flat. So this was specified. So you substitute this value over here. Okay, you please substitute this value over here and get the value of compression force in flange in terms of XU. Now similarly, next step is what? You compute what is the compression force in web. So in web part, so this is my web part. So in my web part, what is happening? If I see, this is the stress block which you have. So I can directly write here 0.36 FCK average stress into this area, so this shaded area. So which is nothing but width of web into XU. Okay, so this is also in terms of XU. CUF is also in terms of XU. So from here you will get what is the total compression force. So total compression force will be CUF plus CU. And next is the tension force. So tension force is fixed. Okay, so tension force we had computed. It is 886 kilonewton, but you have to be very careful with the unit, since this compression force is going to be having the unit of Newton. So I would like to get the tension force also in terms of Newton. So you can do this calculation again, 0.87 Fy AST, and give this in terms of Newton, which is going to be 886 into 10 to the power of 3 Newton. So you compute means you compute neutral axis depth. Compute neutral axis depth C equal to P. So you please do this and give me the value of X.
106.51.
106.5. Let me write down 5 mm. Please confirm, any other students, please confirm this. 106.5 mm, which is more than 100, and which I think maybe it is correct, but others also have to confirm whether this is true or not. Otherwise, I'll 106.5. So okay, so you have XU as 106.5. So what I need to do, I need to confirm my assumption. I said that my depth of flange is greater than 3/7 XU. Okay, so what is going to be 3/7 times XU? 3/7 into 106.5. How much is coming?
45.6.
45.63. So I can clearly see this 3/7, 45.63 mm. So I can clearly see your depth of flange, which is 100 mm, is greater than 3/7 times XU. And also you had computed XU max, if you recall. Here we had computed XU max 268.8. So I can see my XU is also less than XU max. So our assumption is true. Okay, so I can say that this case is valid. So I can write my moment of resistance. So what is my moment of resistance? So you have to be very careful when you write the moment of resistance formula. Why? Because you have the compression force in flange and compression force in the compression force in the web. Now compression force in flange, okay, is going to have different lever arm. Okay, so here if I have this reinforcement, this lever arm is going to be different, whereas this lever arm is going to be different. Okay, so this lever arm is going to be what? D minus 0.5 times YF, and this lever arm is going to be D minus 0.42 XU. So when you write it down, I'll write compression force in flange into D minus 0.5 times YF, okay, and plus your compression force in web into D minus 0.42. So So you can compute this compression force in flange because you already have this expression with you, which you might have done it. Substitute the value of XU, you will get compression force in flange. Similarly, since you have computed XU, substitute here in the compression force in web, so you'll get all these values. So now tell me what is the moment of resistance?
459 kilonewton meter.
459 kilonewton meter. Any other? Let me see. Earlier, what answer you had? What? 371.46. Okay, so I think it will be correct, but you have to confirm.
The same answer.
Same answer. Okay, so this is your answer. Your ultimate moment of resistance is 459 kilonewton meter. Now I'll give you this as an exercise. So here in this question, now what I'm doing, instead of 525 diabar, what I'll be doing, I will go with, rather than 25, let me take this as 28 diagram. Okay. Now tell me what it will be. 6 into pi by 4 into 28. What is going to be the tension force? How much?
4.5 kilometers.
How much? How much? Please repeat again.
4.59.
1. Actually, your voice is cracking. Any other student who can answer? Let me see. 0.87 into 415 into 6.
1333.
Okay, 1333. Okay, 1333 kilonewton. So here you can see your tension force is 1333 kilonewton, and we know the compression force is 864 kilonewton. So you remember this logic of mine. The magnitude is very large for the tension force, so you need more compression area. So you have to bring your neutral axis very much below your depth of line. So it is possible your rectangular part, whatever you have, going to have this rectangular part. Okay, it is going to be what more than the thickness of the flange. Okay, so your depth of flange will be less than 3/7 actually. So you can try with this one rather than this assumption. You go with this assumption and proceed ahead. So you please try this problem. So I'll leave this as an exercise to you all. Okay, and if you want, you can provide your answer in the brainstorming channel itself. So if there is any questions related with the problems which we have discussed, I would like to clarify it. Else I will end this session.